Hi, my name is Melissa Pfeffer. I'm a volcanologist who works at the Icelandic Volcano Observatory, which is a part of the Icelandic Meteorological Office. What we're going to be talking about in this short film is the scanning DOAS technique. This is a technique that we use to monitor the emission rate of SO2 coming out of volcanoes. We do this in collaboration with volcano observatories around the world as part of the NOVAC consortium. The reason that we're interested in monitoring the emission rate of the SO2 coming out of the volcanoes is twofold. The primary reason is that we use this for driving the dispersion models in order to forecast when there might be unhealthy levels of SO2 in the air for downwind communities. The other reason that this helps us to understand what is happening in the volcano and if a volcanic eruption might be expected to start, continue, or end.
Hi, my name is Santiago Arellano and I work as a researcher at Chalmers University of Technology in Sweden, and I'm also part of the NOVAC collaboration.
I'm going to describe the components that are contained within the electronics box. The largest thing you see is the spectrometer. In Iceland, we use a Maya Pro spectrometer because our ultraviolet light is not very good. In other volcano observatories, people are using different spectrometers, which are cheaper and less sensitive than the Maya Pro. Next to the spectrometer, we have the small computer. We are using a MOXA, which means that this is a version 3 of the NOVAC system. On the small computer are the configuration files, which tell the stepper motor how to collect the measurements. And it also contains metadata about the parameters of the station and how you've set it up. Next to these, we see the router, and next to this, we see the sun saver, which is a regulator for the energy that comes in from the solar panels. What you do not see inside of this box are the cable that go to the telescope. You do not see the fiber optic cable, and you don't see the lines that go to the solar panel. When we're running the station, all of the cables are connected. We've disconnected them for the purposes of this demonstration so that it's easier for everyone to see each individual component of the system. Because our electronics box is plastic, we keep our GPS inside of it, but if your box is made out of metal, you'll need to keep your GPS outside. When your system is powered and set up, your telescope is going to start rotating according to the program that you set in your configuration file. Generally, this is done so that the first spectra that's collected is your sky spectrum. This is pointing straight up into the sky. The second spectra is rotated down 180 degrees to collect your dark spectrum, and then it's going to start following the scanning strategy that you programmed, and this is going to be collecting your data.
Now I want to show the components that made the scanner, the optical scanning head of the ScanDOA system using the NOVAC network. You can see it here is rotating. And externally, it has a hood that protects the optics. And I have separated here, in some of the older versions of the scanner, you have the plastic hood with a quartz window. In the newer versions of the scanner, we use a cylindrical quartz window. And the function of this is to, on one side, protect the optics, on the other side, to let through the UV light that we want to measure. The next part is the scanner body, as you see it here. Just a mechanical component which contains the stepper motor on its end. The stepper motor contains one switch which is used to detect the position of reference to align the scanner with a certain position that we select in our configuration. And attached to one of the axes of the motors is this piece of optics. Is just a holder containing a mirror for the conical scanner or the prism for the flat scanner. In some cases, we also add a cylindrical lens which makes the field of view of the optics look rectangular instead of circular. This is a piece of plastic that defines the end of the telescope. All of these components are forming the telescope here. The most important part is perhaps this piece, which is a planned convex lens with a focal length of 7.5 centimeters and a diameter of 1 inch. This is a separation ring that separates the lens from this Hoya filter, which blocks wavelengths of light above 330 nanometers. And then we have the telescope body at 7.5 millimeter focal length. So we attach at the end of this telescope body our fiber. So this is the telescope stop. We add the filter. We put in the separation ring. We now put the lens. We close it. This will go attached into one of the ends of the scanner. The other section is the mirror or prism. Which has a very particular position. Only one position is possible here. This needs to be secure with the Allen key. And when everything is secure with the screws, we can also add the hood or cylindrical window. So we have assembled the scanner of the NOVAC system, and now it's ready to be used for your measurements. Now we are going to configure the NOVAC program for evaluations in real time and for post-analysis. The first thing to do is to go to the NOVAC project in GitHub. This is the open source platform that houses the different projects under the umbrella of the NOVAC collaboration. We're interested this time in the NOVAC program, so we click on the first of these links. And here we can find on the right the releases, the latest version of the software. We click on this and we can now download the software that is compressed in this file. When this is done, we can unpack the folder, and now we will find the different files that are necessary to run the software. The first one, and most importantly, is the NOVAC program executable. We also have the manual as a PDF file that is being updated regularly. The PDF contains information on how to set up the instrument in the field, how to configure the software, how to analyze the data in real time or in post-analysis, and then a number of other files that are necessary for running the software. We double-click on NOVAC program, and on the first appearance it will show completely empty because we have not configured any station. So the first thing we do is to click on the second icon here, configure, or in configuration, and we will see this window that will allow us to set up different instruments. We click on add, and we are asked for the name of a volcano. There is a pre-selected list of volcanoes that you can choose from, but if there is no volcano in the list, we can click on the latest of the last of the options, other. And we are going to use the example of Fagradalsfjall volcano in Iceland. So we have the coordinates of the source here, latitude, longitude, and altitude, as well as the serial number of one of the spectrometers that define the station in our volcano. So we choose first the name here. We can just copy it. We now select the latitude. And the same goes for both the longitude and the altitude of the source. Notice that the coordinates of the source are not necessarily the coordinates of the summit of the volcano. It could be the location of another active vent. We now choose the serial number that defines the instrument in the field, and we copy that as the serial number of the spectrometer. When we do that, we are asked for how many channels there are in this spectrometer. The normal will be either 1 or 2. In this case, the spectrometer only has one channel. That is to say, only one optical fiber is connected to the spectrometer. We are now able to see a window containing information from the station and the volcano. The only thing that is missing here is the name of the site. This is something that you can choose depending on the name that you want to assign to the different station in the field. For this example, you can use something like, for example, Fagra DOAS 1, something like that. The observatory name, we will use the example of the Icelandic Met Office, IMO. The electronics of this instrument is a MOXA. The model of the spectrometer, because it's a Maya spectrometer, we have to choose it from the list. Number of channels equal to 1. And then we have a number of plot options. And what could be interesting to show for observatory practice is the plot flux history, which I will show in a minute. We now click on Global Settings, and here we have to file two things. The first is the location of the output directory, where our data is going to be located. We select one location, here for example, Fagra-Dasfjall. And the second thing is to activate the option to retrieve wind data from the NOVAC server. The wind data is forecast data coming from a model that can be retrieved every day when the software starts every morning, and which will contain information about the wind prognosis for the following hours. So we enable that option, and in this case the file will be reloaded every 360 minutes. This is the basic information that we need to set up for the NOVAC software. We now save this, and we get a very important configuration error, which is saying that we need to check for the reference files in the spectrometer. So where should we find that? In the second page, we have Evaluation Master. And here we can add different cross sections for the different molecules that are absorbing in the volcanic plume. The first of these species must be sulfur dioxide, and we choose the file that it's ending with HP500. This is followed by the file corresponding to the ozone molecule. And finally, the ring spectrum, HP500. If we click on View, we are able to see that the software is reading the files necessary for the evaluation between 320 and 459 pixel number. But this is not the region where we are interested in the analysis. We need to find a region that corresponds to the spectral interval between 310 nanometers and 325 nanometers, which is the standard range of evaluation for the molecule of SO2. We click on Insert Reference, right-click on the file for SO2, and open it with a program like Notepad++ or Excel. And the reason is that we are interested in looking to the line position of the wavelength number 310 and 325. The first of the columns shows the wavelength number. The right column shows the strength of absorption of this molecule, SO2 in this case. And on the edge we see the line number of the different pixels. We look for 310, and we see that it's located in line 572. And 325 is located in the line 872. So we can close this file and simply write 572 for the first pixel and 872 for the second pixel. If we click on View, we can see now the spectral region where the evaluation is going to be performed. The next step is to add information about the communication of the software between the computer that is acquiring the data and the remote station. The Communication tab has different options, for example, serial point-to-point communication to an IP, to a different radio configured for that. One specific configuration for the free wave serial point-to-multipoint, and the most commonly used FTP communication to a IP address and the different credentials to access the MOXA. The rest of the settings can be left as they are. The one here indicates the time taken from the computer time, where the software is going to be in a sleep mode. It will not be actively retrieving any information. We are ready to go. We click on Save, and we are informed that we need to restart the program. Every time that we do any change to the configuration, there will be a call for a restart of the program. Otherwise, the changes will not be saved. So we do that. We just close. So now that we have closed the configure software, we can find in the same folder two new files, configuration and FTP logging, and they are read by the program when you start it up again. So now we can see that there is one station that we have configured, FAGRA DOAS 1, as well as a new tab here showing the flags history in different time windows for the last day, for the last 10 days, and for the last 30 days. This concludes the first part of the configuration of the software. In the next module, we will look at how to look at data, how to evaluate the spectral characteristics of absorption in the plume, and how to get fluxes out of scan measurements. When we have configured different stations in the field, we can first check if the information that we have given in the CFG file of each instrument is correct. A nice way to do is to use the NOVAC software for that. So I'm going to show you how to check the setup. We go to Analysis and click on Setup. And then we choose different evaluation logs for the stations that we have installed in the field. For example, I have this example on FAGRA Dalsfjall, one day in August 2021, and we have 3 stations with a serial number ending in 27, 37, and 02. We click on each of these, the evaluation log file, which will now select all the scans collected by this specific instrument on this specific day. What we're looking here is the location of the volcano, shown in red, and the location of the station in this point, as well as the projection of each of the measurements taken by the instrument in one scan. This is a flat scanner, and therefore the projection looks along the line. If we select now the second of the stations, evaluation log for this spectrometer, we see the conical setup corresponding to the instrument 37. And we repeat the same for the last of the stations, which is also a conical instrument, orientated in a different way. If we click on each of these scanners, we can read out both the distance to the volcano as well as the direction of the azimuth or compass that has been set up in the station. So in this way we can identify if the information that we have included in the CFG file is correct or not. Because if it will be incorrect, for example by 180 degrees, we will see the compass of each of these stations rotated. Instead of 125, for example, 305, a scanner that is orientated away from the volcano. Therefore, the correct information is 125. We could also plot the direction of the sun, shown in these yellow lines, and go through all the measurements taken on the day and see how the sun position is changing during the day. This is the best way to check the setup of the instruments in the field. It is also useful to check how the data look like when we have done an installation in the field. The easiest will be just to set up an instrument connected with your laptop and open the NOVAC software. And I will show you how to look for the pack file and see if the information on each scan is logged correctly. Check pack file. We select a number of pack files. For example, in this day, we select one of these stations. We select one of the stations, and then we can see a list of pack files collected in the field, and we can choose one of them taken close to noon on this specific date. And we can see here is a plot showing the pixel number and the intensity of the spectra in the one scan. The first spectrum corresponds to the sky measurement, and you can see that it's a nice spectrum with a darker zone close to the 300 nanometers and lower, and increasing up to the intensity that corresponds more or less to 50% of saturation in the spectrometer. The next spectrum in the sequence is the dark spectrum that looks flat, and all the subsequent spectra are taken at different elevations angles in the same scan. So the spectral information looks correct in this example. We can also look at the different information logged, for example, the view angle as we select the different spectra. We can also see the information about the GPS, which logs the date, time, and position of the scanner. And we can see that it's correct information, changing with time, but keeping the same position, and so on and so forth. In this way, we can guarantee that the data that we have collected in the field is logged correctly. In this exercise, we're gonna look how to make a spectral evaluation of the data. The most important consideration is to have good spectra evaluated at the right spectral band. And what I mean by this is, for example, data that corresponds to volcanoes with very weak emission. We should look into a more sensitive region between 305 and 315 nanometers. When the source of emission is very strong, on the other hand, we may look at the longer wavelength regions, even at the 360 nanometer wavelength region. So we will look into this by clicking on Analysis and choosing Re-evaluate. We first browse files and select a number of files that we want to re-evaluate for one of the spectrometers. We can go through each of these scans and inspect how the data look like, the same way that we did with checkback file, but in a more compact format. The next step is to select the fit window, and let's say that we choose the region between 310 and 325 nanometers, which we already looked for in the file. This was located between pixel number 572 and pixel number 872. We can now choose the solar spectrum, and this is a spectrum that is used for correcting the spectral shift in all the measurements. So each measurement will be compared with theoretical solar spectrum that has been adapted to the resolution of the spectrometer, and in this way correct for possible shifts in the data during the measurement. We can then use the solar spectrum. The solar spectrum is, in this case, a synthetic spectrum of the sun that has been adapted to the resolution of the spectrometer, and which could be used for performing a spectral shift between the theoretical solar spectrum and the measured spectrum in the field. In this way, we can correct for each of the scans possible drifts in the wavelength pixel mapping. We select solar spectrum from all the reference that corresponds to our spectrometer. In this case, this Maya spectrometer has a solar spectrum here. And now we add different cross sections for the different molecules absorbing in the spectral range of interest: SO2, ozone, and ring. We can again inspect the spectrum, they look okay. In the MISC section, we are interested in looking at all possible conditions of measurement. We let all the pre-selected options unchanged, but we click on Don't Ignore Anything for that spectra. And then we look at the evaluation of each of the spectra. We can pause to see it very finely to evaluation. And now we see on the left side the resulting fit spectrum, and on the right side the comparison between the differential cross-section of the measurement in red and the theoretical cross-section in blue. So it's a very fine fit of SO2, which shows the column value, the shift of the spectrum respect to the solar spectrum, as well as other parameters that have to do with the quality of the fitting. We can also check how the fitting looks like for the other molecules, for example, ozone and ring. In this case, a very weak signal for these two because the measurement is taken in very close succession of each other. We can go through the next spectrum in the same scan and see how the fit look like. And if we want to run this for a number of scans, it will take a long time, so we can just unpause the evaluation and run it all the way through. So we can see these bars showing the progress of the evaluation for each individual scan down here. and for the collection of all scans that we have selected in the upper bar. The result of this evaluation will be a new file called re-evaluation, which will create a new evaluation log, which can then be used for analysis or calculation of the flags. So far we have made different steps coming from the installation of the software, the configuration of the different stations around a single volcano. We have then inspected the setup of all the stations around the single source using the setup function. We then check also the quality of the pack files. For example, when you have done an installation in the field, you connect the laptop to the instrument, and then you select check pack file and see how the spectra and the log of information is working. And when we do the operation of the data, we have first analyzed the re-evaluation, how to make new column evaluations out of our scan measurements. And in this last part, I will show you how to calculate the flags from this re-evaluation log. We go to Analysis and we select Flags. The first thing is to add an evaluation log for one specific instrument. And we can look, for example, to the case of Fagradalsfjall. We have created this re-evaluation log and we just upload it here. We can see a sequence of different scans taken by this instrument on this date. If we go back to the first of these, you see the distribution of SO2 columns with the scan angle from -90 to +90 degrees. Red bars for SO2 column, white bars for the error in the fit, yellow dots showing the intensity of the solar spectrum in the region of analysis of evaluation for SO2, and white dots for the intensity of the spectrum in the highest point of intensity, of peak intensity in the spectrum. The yellow dashed line shown here marks the angle of center of mass of this plume. This information is used to locate especially the plume. When one of the scanners, for example, finds the plume at this angle and another scanner finds the plume at this angle, we can use this information and triangulate and get out of this both the altitude of the plume and the plume direction, which are parameters used for the calculation of the flags. We now need information about the plume direction, plume height, and plume speed. The information about plume direction and plume height can better be obtained from this triangulation routine that I just explained. And this is located in the same file containing the data for this day called geometry log. The geometry log lists different measurements taken by two instruments at the same time or within a certain period of time. And it shows for each of these instruments the angle of the center of mass of the plume and the calculated values for the distance to the plume height above the first of the stations, the plume height above the sea level, the error in the calculation of the plume height, as well as the wind direction and wind direction error. Based on this information, we can also add information about the wind speed. The wind speed is for now a parameter that is obtained most often from external sources of information. It could be a weather station located close to the volcano. It could be a meteorological model run by the observatory, or it could be a global model from one of the services, meteorological services. We have created a file that should look like this. Is a notepad file containing the date, the time, and the expected wind speed, wind direction, and plume height defined above the instrument that we are analyzing. With this, we come back and select this wind file from Import Wind File. We locate it. And now you can see in the section down here that the parameters for the wind will be shadowed because they will not be selected by the user, but they will be read from this file directly. So we can calculate the flags for this scan, for example, 304,000 meters. So we calculate now the flags for this scan, in this example, 3,900 tons per day. We can go through the next one and calculate it. and so forth with the rest of scans. We could also automatize this process and just select flags for all scans which see the plume. There is a warning showing up here indicating if you're sure the thing that you're doing. We click on yes, and then now the program will go through all the scans selected for this specific instrument on this specific date. The result of this will be a new file for the evaluation of this specific file called post-flux log. And as you can see, the post-flux log is a time series with the date, the time of start and stop of the scan, and the flux that has been calculated, in this case in kilograms per second or in tons per day, for each of these scans. We can report now the time series of emission of the volcano out of this file, and we can also use some of the parameters that are logged in this file to define the quality of the measurements. For example, we can look at one of the last of the parameters here, showing the completeness of the plume, and based on the knowledge that we have on the measurement conditions, we can define a threshold for this value. For example, something between 0.7 and 0.8 and above is a good value for the plume completeness. It is also important to look, for example, at the center of mass of the plume, because the plumes that are located within a certain range above the instrument have a better conditions for the measurement. So we should pay more attention to the flux data that is related to the measurements within a relatively narrow field of view above the instrument. I want to show how to make sense of the data that we have collected from the instrument. And what I mean by this is how to relate the setup of the different instruments looking at the plume at the same time with the data that is obtained from these instruments. If you remember, the tool called Analysis Setup allows us to explore the different configurations of the instruments in the field. For example, we select for this date, August 2018, evaluation logs from 3 different instruments, and we can see the plot of how they are configured respect to the volcano, which is this red dot here. At the same time, we can open another program and look at the data that was collected in terms of column values. And we do that by clicking on Analysis Flags, and we can select, for example, the first of these stations. We see the collection of scans, and we see that it's a very strong plume, slightly moved towards the left edge in some scans. The plume direction is changing over time, so the center of mass is also drifting a little bit. But the scans are almost complete, have a good shape and very strong columns. How it looks like for the same date, but different stations. For example, this one, the 27 station. We see that the distribution of columns is much lower, and they are seen on the right side of the window. So we go through these all the time, and we see the center of mass is located on the right side. When we see the serial number of this instrument and we relate it with the setup, we see that this instrument is the flat instrument here, while the first instrument is the conical instrument here. So we see that the plume seems to be going relatively above one of the stations, but on the very edge of the second one. And this is consistent with the observation of the column position here. What will happen with the last one is that the plume is located on the other edge, because the plume is located south of the first of the stations. So while one of the stations sees the plume above it, the other station sees the plume on one edge, either the left or the right, depending on the direction of scanning. The information in these scans may not be good enough to use for the flux calculation, but is good enough to be used for geometry calculations and to locate especially the position of the plume.
Thank you so much for watching the video. We hope it's going to be really helpful for you as you monitor SO2 from your volcanoes.